Hi everyone. The talk I gave today is called Vetting Single Sign-On SDK Implementations by Symbolic Reasoning. This is a joint work with Ronghai Yang, Wing-Chun Lau, and Kehuan Zhang. We are from the Chinese University of Hong Kong. Since the first author could not come for the visa issue, I will present this work instead. In recent years, we've seen strong adoption of single sign-on services. With single sign-on, a user can conveniently log in a third-party service with a single ID and password. For example, you can use your Facebook account to log in an IMDb website. According to a report, more than 75% of users prefer using single sign-on, and more than 90% of them are satisfied. Previous study also reveals that many web applications and Android applications also support single sign-on services. Let's see how single sign-on works. Basically, it involves three parties. The third party application, which is also called the reliant party, the identity provider, and the client device. When a user tries to log in a RP server, the RP server asks, "Who are you?" And the user tells an IDP server, "Please tell IMDb my identity." And then the IDP server returns the user's identity proof to the user. And then the user gives this identity proof to the RP server. And when the RP server receives that, and the RP server says, "Welcome." Okay, so under the hook, here's the single sign-on protocol flows. In step 1, the user initiates the single sign-on process with the RP server. And then in step 2, the RP server responds with a redirect URL and a state parameter to prevent cross-site request forgery. And then the user will be redirected to Facebook. And in this step, the user is authenticated to Facebook and grants some permissions to the RP server, like the public profile and the email address. Then the IDP will return a code, which is an intermediate proof of identity to the RP server by this user. After that, the RP server approaches the IDP server with the code and its own credential to exchange for an access token. So with this access token, the RP server can get the user's profile, like the email address or the birthday, from the IDP server. So at the end, the user can request her information on the RP server. Okay. So as we discussed, the entire process is quite complicated. It involves multiple parties and multiple operations. Therefore, SDKs are provided to help RP developers to implement single sign-on services. Actually, the SDKs are provided not only by IDPs like Facebook, but more often by fourth-party SDK providers for cross-IDP support of an application. As you can see in the table, some SDKs enjoy millions of downloads, like Request OAuth library and OAuth library, and those numbers are just conservative estimate, and the number of downloads are by the developers, not by end users. So if these SDKs are not secure any applications using the SDKs will be insecure. Unfortunately, we have seen many attacks due to incorrect implementation of SDKs. As you can be seen in this example, the RP server-side SDK only checks the user ID but does not check the access token at all. On the other hand, we noticed that in the literature, most existing work does not analyze the single sign-on SDK implementations. So one direction is formal analysis of single sign-on protocol standards. The approaches include model checking and cryptographic proof. The other direction is to detect real-world vulnerabilities by treating the SDKs as a black box. So the techniques include network traffic analysis or model-based automated testing. Besides, a related work is to discover the hidden assumptions that are required for the proper use of SDKs. But this work requires that the code has to be manually translated. So, however, little efforts has been devoted to a systematic testing of implementation flaws in single sign-on SDK internals. Therefore, in our research, we raised this question: is a single sign-on SDK vulnerable by itself? In other words, do they still work properly under whatever inputs from the attacker? In our work, we focus on logic vulnerabilities of the RP server SDK internals. So in our testing, we control the request like those in the figure. We assume that the attacker can lure the victim to visit a malicious RP server in order to obtain a valid access token of the victim's IDP account, but this token binds only to the malicious RP server. And the attacker can also set up an external machine and use her own credit account to communicate with the client, the IDP server, and the RP server. And we also assume that if HTTPS is not used, the attacker can eavesdrop victim's communication. So we developed a tool called S3K Vector. It plays two roles. First, in order to support the protocol flow, it interacts with RP server and IDP server as if it is the client device. Second, to provide the input to the RP server, it communicates with the RP server on behalf of the attacker. The high-level idea is that, first of all, we extract all the program paths from the SDK using concurrent execution, and then we define some security properties for single sign-on SDKs. Those properties are essentially the expected behaviors. At the end, we check whether the security properties hold on every program path. However, to concurrently explore the path, we encountered some technical challenges because existing concurrent execution framework do not support multi-party communication and multi-lockstep operations. In particular, the problems we're facing are that some non-parameters like code or state can only be used for once. Besides, some parameters are remotely generated and consumed by the remote server. So with these problems, extra effort are required to create inputs to properly feed single sign-on SDKs. Existing approaches also have some issues and cannot address our challenges. The first option is to run the external functions of SDK concretely. However, we can only make limited API calls to the IDP server because it imposes limit on API access rate. Therefore, this cannot correctly generate nonce parameters. The second option is to return a random value of the same return type of those external functions without execution, like those techniques used in Dart. However, this will cause false positives to our testing result. Besides, symbolically exploring the external functions is not feasible because we don't have access to the source code of those IDP servers. So in our design, S3K vectors consists of 3 modules. The input is a compiled SDK, and we then break the order of request and coordinate multi-party communication during concurrent execution. After that, we extract the predicates and represent them as a tree, and then translate the tree to a set of logical formulas. So at the end, we verify whether there are any violations against the security properties that we input. So for request order scheduling, we use a single and simple scheduling algorithm. Let's see, originally the request order is request 0, request 1, request 2. Since we are only interested in our algorithm will generate all other possible schedules. Since we are only interested in the authentication property, which is completed by request 2. So other schedules also end with request 2. So after that, if we break the request orders, we need to coordinate multiple parties. So our approach is to simulate and modify the external world for the SDK. In particular, it generates a nonce parameter internally on behalf of the IDP server. And if this nonce parameter satisfies the condition of the path to be explored, then we use this nonce parameter. And if it does not satisfy the conditions, we will locally solve the condition and use a new nonce parameter. So for example, after path 1 is executed, the code is invalidated. To explore path 2, we will generate a new code. If this code satisfies the condition, we then use it. For path 3, we still use the previous code, but it does not satisfy the condition, then we'll solve the constraint and generate a new code, which is none, because the constraint is that code length should be 0. Okay. After that, we combine those paths as a tree. Each node is a condition. And we then represent the predicate tree using SMT library language. For each path, we just use AND operation to combine those predicates. And here is the security properties that we defined. The key observation is that an RP server should log in the user if and only if the exact user has actually authorized this RP server. To ensure this, we defined some clauses. The first clause means the user stored by the RP session should be the owner of the received access token. So does the code and refresh token in clause 2 and clause 3. Clause 4 and 5 ensure that the access token and refresh token, like here, should be passed to the intended RP, but not to other RP servers. Clause 6 means that the final logged in user should be the one who authenticates and authorizes with the IDP. Using S3K vector, we discovered 7 types of vulnerabilities on 10 popular SDKs. 4 of them are previously unknown, and the consequences are that the user's account could be hijacked in the RP, for example, due to the access token injection that we discovered. The other consequence is that the user's activity can be sniffed in the RP due to the use before assignment of state parameter that we found. As can be seen in the table, our tool supports both implicit flow and authorization code flow. Compared with the baseline, which uses concurrent execution tool Z3, our tool achieves 2 to 17% higher statement coverage and 2 to 19% higher branch coverage. And our improvement has enabled us to discover 8 more vulnerabilities. Here are the vulnerabilities that we found. Existing classes of vulnerabilities include token substitution, no check of TLS, like misuse of state or no use of state parameter. The new vulnerability types include use before assignment of state parameter. This could allow sniffing of victim activities by cross-site request forgery. The other 3 types are bypassing MAC key protection, refresh token injection, and access token injection. These vulnerabilities could allow an attacker to hijack victims' account on the RP server. And we reported all these newly discovered vulnerabilities to the corresponding vendors, and they have all fixed them. Here we show an example of vulnerability in the code snippet. The code parameters is stored, and surprisingly, this access token is also stored. If on the RP server, if an attacker attaches the access token in the URL and sent to the RP server, this access token is then stored by the SDK and used for authentication later on. So to exploit this vulnerability, attacker just need to set up a malicious RP server and lure the victim to log in and to get the victim's access token. And the attacker can then inject the victim's access token to the RP server. And then the RP server use this access token to request the victim's to obtain the victim's resources hosted in IDP. So the IDP thinks that the current user is the victim, but the RP server thinks that the current user is the attacker. So the attacker, after that, the attacker can log in the RP server as the victim user. So to conclude, using S3K vector, we conducted a measurement study and have some new findings. In particular, we performed an in-depth security analysis on 10 popular single sign-on SDKs. We found 7 types of serious logic vulnerabilities. 4 of them are previously unknown. And we also developed a tool to discover vulnerabilities in multi-party systems. We have some new techniques like scheduling the request orders and coordinate multiple parties. And our technique can also have other usages, like can be used in payment systems and etc. And that's it. Thank you.